welcome everybody to today's deep seminar. We are very happy to have Katarzyna Sznajd-Weron. So Professor Weron did her PhD in Wrocław, and then after some years working in the University of Wrocław, she moved to the Technical University. And she is a pioneer of applications of statistical physics to sociological systems, for which she received a number of recognitions and awards. And today we're happy to share this knowledge, and she'll tell us about private truth, public lies within agent-based modeling. So please, Kasia.
Thank you, Piotr, very much. Thank you for this invitation and for a very nice introduction. As a pioneer, that sounds nice and ugly at the same time, because it seems that I'm already really old, but that's true. Okay, no, I'm not really pioneer, but yeah, indeed, I joined this area at quite a beginning, not really beginning, but quite early, let's say. So this subject I will be talking today is related to the project I'm conducting, I'm leading right now, and it is in this panel from our National Centrum of Knowledge in this social panel. So this HA6 is devoted to sociology and social psychology. So this is the subject that is interesting also for social scientists. So what is this private truth and public lies? Let me give you an example from my private life. So imagine that your colleague invites you to the party at her home, and you see, and she's showing you this interesting, let's say, Christmas tree, and ask you, how do you like it? And many people around you seems to be really happy with this Christmas tree, and the response, oh, it's great, so beautiful. And you are looking and you think, a bit weird, but what can you say? So what would you answer? And this is exactly what happens usually. Maybe you will answer, oh, it's interesting, or it's original, maybe. And this is what we call preference falsification. So the act of communicating your preference or your opinion that is different than your true one. And as you may imagine, the main reason for this is that you believe that your expressed preference or opinion will be just more acceptable socially from different point of view. Maybe because you don't want just to hurt your friends, or maybe just that you don't want to seem like uneducated or anything else, but you believe that it will be more acceptable. And as you may imagine, also it has huge political and social consequences like revolution and so on. So this title that I gave for this talk, this private truth and public lies, it comes from Timur Kuran's book. And also this example that was from my own life, you can find a very similar example in this book by Timur Kuran. And this is the book in which he named just the lie. He invented for a lie this nice term, preference falsification. So it's a lie, but for some reason. I mean, each lie is for the reason, but this reason is very particular one. So you believe that this is just more acceptable socially. So to model this kind of things, you need opinions that are on both levels, like public and private. And of course, I will go into details during my talk. So first of all, I will tell you why I am personally, or my group is personally interested in preference falsification. Of course, it's interesting itself, but we are interested in this subject for a specific reason. And so for specific reasons, so what question we are asking, that will be another thing I will tell you. And how do we want to answer this question? As you saw from my title, we will use agent-based modeling. So we will use agent-based modeling to ask the question, but specifically. So I will give you the example of the model within which we want to answer this question. And in the end, why we should care about all these things. So let me start. So inspiration came from two sources for this preference falsification. So first inspiration came from my colleague, Paul Nail, who is social psychologist, experimental psychologist from United States. And he invited me like in 2016 to write a chapter with him to this book of the psychology of consumer and social influence. And then we started to collaborate, and he told me that he saw some papers on social influence, but he's missing still some social responses. So based on his model in psychology, I built a model that is more structured, like agent-based model. And in this model, I had these two opinions on the private and on the public level. But it was in 2018. I was not really happy even with this paper and with the model. So I gave up it for a while. But then I started to be interested in something which is called social hysteresis. And then I discovered that maybe this preference falsification is something that will be really useful to understand social hysteresis. So this is my next motivation that I'm doing this grant. And one of the, let's say, direction of my research is related to preference falsification. So what is the social hysteresis? We are physicists here, so we know what the hysteresis is, but I'm showing this picture over and over again because it's so beautiful. It's not my own picture. As you may see, it comes from this paper. And it shows not human society, but the spider society. But it is so beautiful that so we have the spider society, and the spiders can be in two states. The society, in fact, can be in two states. So the one state is like, you see aggressive society, and this is the red one. And the second state is that you see this calm, let's say, society. So in this calm state, spiders are interacting friendly, collaborating with each other, and here are just fighting. So what they observe that till some temperature, they are always calm, but if initially they are in the calm state, you have to heat them up until the temperature T2, and then they will flip to this aggressive state. Whereas in the already in aggressive state, you have to cool down the system until the temperature T1 to make them calm again. So at the beginning, I saw this picture and I thought, maybe it's just the like personal hysteresis, that I'm just angry or calm depending on the temperature. But it occurred that this similar studies are done with people, and what occurs that really aggression is like virus. So of course you need certain conditions like the temperature, but then maybe one person can be the source, and then this aggression spreads like virus. So it's really collective behavior. And of course it doesn't have to be temperature. It can be any not any, but many other external factors. Like here, for example, you have predation risk, again, animal society, but also the social hysteresis is seen quite often in human societies. And in particular, empirical studies suggest that, for example, public opinion shows hysteresis and tipping points also. So it means that it remains seemingly resistant to some changes, the external changes, but then you see this abrupt sudden shift. And hysteresis starts to be particularly popular recently, because as you see this quote from this paper, hysteresis is really a nice concept, versatile concept for volatile times. So if you have any types of crisis, So before we had COVID, now in Poland, we especially feel this war in Ukraine. So in this type of situations, this hysteresis is particularly, let's say, important idea. But also what is very, very interesting, people are doing really experiments on humans. So here you have an example of the paper from Science from 2018. Baroncelli, who is physicist, was one of the co-authors of this paper. So this is like, again, interdisciplinary team. And they showed evidence for a tipping point in social convention. Recently, in this last year, I guess, they published another paper with another empirical results. So there are also experiments that are showing that you see mostly tipping points, because hysteresis is not that easy to see. But why I'm combining these two things together? Okay, before I tell this, I will tell what is then my question. So why I'm interested in preference falsification. So in fact, I would like to answer what factors can promote and what are against, or what can hamper social hysteresis. Because understanding social hysteresis can help us to understand many different problems, which I will tell at the end. And we will look for this answer within agent-based models. What I mean by agent-based models, probably most of you knows, but just to remind, because Piotrek told me that for him it will be not understandable at all. So I just the quick. So you have the system. It can be. It can exist on some regular lattice, or maybe in some social networks. So like it's modeled by graph usually. And usually in the nodes of this graph, you have agents. Here, as you see, you have very simplified agents, like in the Ising model, spins up and down, which can, like in the voter model also, that was one of the subject of this seminar, that you have opinion like you are in favor or you are against. So you have these agents, and there are some rules of interactions. So like in the Ising model, you have Hamiltonian that tells you how this spins interacts. And in agent-based models, it can be Hamiltonian, and it can be even called some disagreement function or something like this, but it can be also just some dynamical rule. So instead of giving Hamiltonian, you give some dynamical rule, because of course, not all this system has to be equilibrium system. So you have usually some dynamical rules, and I will give you this dynamical rules for our particular model. And you have some agents. They can have more properties, not like being just the spin that is only up or down. They can have some personal traits, but the models I'm dealing with are usually very simple. And you have some environment, as I told you. It can be some real social network. It can be some model, so some graph. It can be even regular network, and these interactions. Okay, so we will answer with an agent-based model, and why I'm telling about tipping points, also sometimes about critical mass and hysteresis at the same time. Because from the theory of phase transitions, we know that we have only two types of transition in the world. We have, recently we talk about hybrid, but from the Landau point of view, we can talk only about continuous and discontinuous phase transition, because our order parameter changes only continuously like here, or discontinuously like here. If you have continuous phase transition, you cannot expect any hysteresis. Hysteresis is impossible. You cannot have hysteresis. Also, you don't have any critical mass. You don't also any latent heat, so you don't have energy involved in the transition. So you really see the difference. Of course, you have many other things like scaling, power laws in correlation functions, and many other things, but this is not what is important for us right now from the social point of view. But this lack of hysteresis and the critical mass is something that is important for us. So if you are talking about hysteresis or the critical mass, you have to look at the discontinuous phase transitions. So we have discontinuous phase transition. Of course, you have hysteresis, that's the one thing, but also you have the critical mass. In what sense? That, as you see, that like your final state depends on the initial state. So if you are, maybe I will make the pointer like, so if, for example, I will start with, for this P, which is some external parameter, I don't know what it means, but if I start from this concentration, that is somewhere here, so then I will end up at this line. So like, let's say disordered phase. Whereas if I start from here, I will end up on this point. So starting from a given concentration, so that's why I'm talking about critical mass or about the seed, like in the supercool water, we can supercool it like to -40 degrees. But then, if of course you put a grain of ice, it will freeze immediately. So like here, you need some critical mass to of course, in this range of hysteresis, to reach a given state. Okay, so simply, I'm a physicist. So if I want to find the answer, where can I find hysteresis or critical mass? I will just look for discontinuous phase transitions. Of course, not with every discontinuous phase transition you will see hysteresis. I'm aware of that, but certainly I will not see it in the continuous phase transition. So how to build a model, agent-based model, in which I will see hysteresis. So if you look at the equilibrium statistical physics, you already know what to do, because we know, not always, but we know something at least. Like, because we know about universality classes for continuous phase transitions, but we also know that we have the models like the Potts model, that, for example, that if we increase the number of states, like having, instead of having just two states up and down, we increase the number of states, then we can expect discontinuous phase transitions. So we have already some knowledge in the world of equilibrium statistical physics. What can hamper and what can influence the type of the phase transition? In the world of non-equilibrium physics, it's not that obvious, although we also know something already, but not that much. So okay, so of course, how we can build it, if we introduce some kind of a memory to our agents. So a memory means inertia on the individual level. Of course, then you can expect that probably it will be also visible on the macroscopic level, because hysteresis is nothing else like the inertia of the system. But of course, like, it's surprising for social scientists, not that surprising for physicists, that even more memoryless agents can also produce hysteresis. Of course, now you can say it depends on the definition of the memory, but seemingly memoryless agents, and I will show you what I mean by memoryless agents, can also show hysteresis. And it depends, like, the hysteresis can appear if you increase the size of the group of influence, and I will talk about this in a minute. If you increase the number of layers in social networks, like, for example, here you have an example of multi-layer network. So imagine that you have contacts on Facebook, you have another contacts on LinkedIn, and you have another contacts in face-to-face contacts. So then you can build multi-layer network, and then the number of layers in the networks, of course, also increases. The possibility of hysteresis in a different way than the size. It's like having the number of particles in which we interact and the different dimensionality also. It's not like, if you think about, for example, percolation, its dimension gives something different than just the number of neighbors. But what I will talk about today that also some hidden preferences, so like prefers or specification, can induce hysteresis. Okay, so now I'm going to the model, and the model is very simple. This is the original model we proposed in 2018. So how it works? Maybe I will only change this pointer. Okay, so we will deal with agents in the nodes of a given graph, and each agent can be each agent has public opinion, which can be in only 2 states, and the private opinion, which also is in 2 states. So like in favor and against, let's say. So in total, we have 4 states of each agent. So you have private, which are kind of internal opinions, and public, which are external opinions. So first of all, only this is our assumption, but it's quite logical assumption that only this public opinion can be seen by others. So I denoted by this darker color the public opinion, so like private is a bit hidden, so others cannot see this private opinion. And we introduced 2 types of social response. One is so-called independence, and second is called conformity. Conformity will be the force like for magnetic interactions in the Ising model, that you will try to follow others. And I will explain it in details in a minute. And independence will be behavior, like independent behaviors of others. It will be not exactly like the temperature, because if you think about the temperature, you then think about the free energy, and you think about competition between this interaction and the temperature. So here we will not have this competition, we will just have some probability that you act independently of others, so it's a kind of noise in the system. Conformity, if you think about opinions that are on the private and on the public level, can take 2 forms. So one form, which is really well known and confirmed by many examples in social psychology, is so-called compliance. And I will show you what compliance is on the next slide. And then another type of conformity, which is related to the fact that we have some private beliefs also, is so-called this inhibitory contagion. And this is also related to type of frustration that sometimes we have when we act differently than we would like to act. So I will tell you about this also. And this is, in fact, this inhibitory contagion is one of the favorite types of conformity of my friend Paul Nail. So this is the first social psychologist I've been working with. Okay, so 2 types of conformity. First, compliance. Compliance is the kind of conformity that is expressed only in public. So you don't have to accept something privately, but you publicly conform. And the most famous example, and one of the first examples of this type of conformity, was conducted by Ash in 50s. And this is the experimental setting. So he was showing these lines, so like these 3 lines and this 1 line, and you had to point out which of these 3 lines had the same length as this 1 line. So the important thing is that the experiment was conducted in several settings. So first, you were the subject of experiment was alone in the room. So, and he or she has to answer, and they were collecting how many errors was made. So it occurs that it was like quite obvious how to recognize, how to answer the question, because almost no mistakes were made. And then another setting was that the subject of experiment, this guy, was in the group of others, and all these others were helping just the researcher, but of course the subject of experiment didn't know about this. So the experiment went like this. So these lines were shown, and then the first guy was answering, and he was giving the right answer, the second right answer, right answer, right answer. So the subject was also giving the right answer. But then in the third turn, it occurs that this guy gave for example, the answer that the first line is the most similar. Then this guy thought maybe not, maybe third one. So the third one is the most similar. Then this one also answered the same, and this one answered the same, and this one answered the same. And then the subject of experiment was also very often answering against his, let's say, beliefs. Why we know that it was against his belief? Because when the same experiment was made in different conditions, so like he could just write on the piece of paper instead of expressing publicly the answer, this agreement with the group dropped down drastically. Also, with another setting, when he had like one friend in this group, in a sense that not really friend, but at least one person was giving the correct answer, also the person of experiments was giving the correct answer. So it occurs that the first thing, the size of the group of influence increases conformity, but also unanimity is crucial. And what is also very crucial, that it is only in public. So this is one type of the conformity they observed. And for this, we will use this unanimity rule, which is really important. And the second type of conformity is like this. So imagine that you are on the party, you are not dancing, nobody is dancing, so the floor is completely empty, but you would really like to dance. So now you are in this internal conflict. You are shy, so you don't start to dance, but you would like to dance. So then even a single person can influence you to dance because you already wanted to dance. So it's immediately contagious. And this is the example given by Paul Nail in our paper. And I really like it because it really shows how it works. And this is simple as that. So this is important for this model with two opinions, if we are in internal conflict or not. Okay, so let's go with how the model works. I asked this version of the model act then think. I will explain you why in a minute. But for now, just stay with this name. So first we will update the public opinion. So that's why act. And then we will update the private one. So we have, this is example of a given graph. This is a small graph. Of course, we are dealing with much larger graphs, but this is just an example. And you, at each update, you choose one voter at random. Let it be this one in the yellow circle. And you update the public opinion. So how you update this? You update it according to the rule of so-called Q-voter model. This Q-voter model, sorry, I didn't give the reference here. It was introduced by Castellano and others in the paper in Physical Review E in 2009. So we will update this. We will use partially this Q-voter model here. So okay, so I have chosen randomly one agent. Let it be this one. And first, with some probability, independence can act. In the case of independence, you just replace the public opinion by the private one. So this is already a bit different from the original Q-voter model. In the Q-voter model with independence, you were just flipping randomly. But now we have these two opinions, private and the public. So independence should work like this. So if I have my private opinion different than my public one, and I am independent at the given time step, I will just replace my public by the private one. So after this update, you will see this state of the agent.
Sorry, can I ask?
Yeah, sure.
So is that with the probability, or it's 100% probability of flipping? Or?
No, it's probability. So, but this is a very good question, because we can make it like in two ways. Let's say we call it annealed and quench approach. So one possibility is that we set forever some agents to be independent, some others to be conformist, and then with like probability 1, if you choose independent agent, he will change like this. But in our setting, we have just some probability that is a parameter of our model, and each agent can behave independently or conform. So in a given time step, I'm choosing the number between 0 and 1, and I'm checking if it's smaller than this p or larger. If it's smaller, I know that independence works, so I behaved independently. If it's larger, I'm not independent, and then conformity will work. So this is like, I will change I will change if I'm already independent. So first I'm checking if I will behave independently, and if I am at the given step independent, I will behave like this. Is it?
Yeah, thank you.
Or, yeah, thank you. So thank you for this question, because I think that many others maybe also had the same doubts. Okay, so but suppose that we have chosen this R larger than P. So in fact, because we have this independence only with probability P. So what then? So let's go back to our original state. So we didn't, this independence did not work, and still conformity can work with complementary probability. So with probability 1 minus P. If conformity work, then we pick randomly Q neighbors without repetitions. And the Q is another parameter of our model. So we have already 2 parameters. In this example that I'm showing, Q is equal to, just to give an example. So we are choosing these 2 guys, for example, can be anything else, but I'm choosing only from the neighbors. And the neighbors are all these guys that are connected to our agents. So in this case, we have like 1, 2, 3, 4, and that's it. This guy has 4 neighbors, but I'm choosing only 2 because my parameter Q is equal to. Okay, and now this is this tricky point, let's say, because I'm checking if I am in internal conflict or not. So here I see that, yeah, indeed I am in internal conflict, because privately I'm in favor, but publicly I say, no, I'm against. So if I have this conflict, then this inhibitory contagion can work. And then it's enough that only one of my chosen neighbors in this group has the same opinion that I have private. So I see that this guy indeed publicly say, yes, I'm in favor. So I will change my public opinion also to the green one, to the in favor one. So this is how it works. In the case I'm in internal conflict, but it can happen that you choose another guy. Like for example, let's imagine that we have chosen this guy, and also conformity worked, and we have chosen, for example, okay, I will replace again with a pen. So imagine for a while that I'm choosing this guy and this guy. So now they are publicly in different states, and I am in internal harmony, so I will not change. But if I'm choosing these 2 guys that are in this brown circles, then they are both in the same states, and then I'm influenced. So this is this compliance. So I will publicly agree with them, and I will turn to red. So this is how this procedure for the public opinion works. Whereas for the private one, it's much simpler, and it's exactly like it was originally. Sorry for this text, it should not be here. I don't know how it appears, but okay. So in the case of private opinion, it works like the original Q-voter model. So now we are at the stage that update the private opinion, and in this stage, what we do, we still can have independence with some probability P, but in this case, we just flip to opposite direction with some probability. Usually we take 1/2, but it doesn't matter really. until it's larger than 0. Because if it's any probability larger than 0, then we can rescale all these results, and it was shown by in one of our papers. But yeah, it's quite trivial. And now how conformity works. So now we have conformity with complementary probability again. Now again, we are picking Q neighbors without repetitions. And now if they are unanimous, then I will change my private opinion to this opinion. So
sorry, can I do something?
Yeah, so this is a bit stupid. That's why I flip it so quickly. Please ask a question.
Sorry, it's just the difference between public, updated public and private is this unanimous.
Yeah. So in case of changing my public opinion, I could be also in this conflict. So then one guy having the same opinion as me, like publicly, could influence me. And now with the private opinion, it cannot be like this. I always need unanimous panel to be convinced. So this is the difference. But in fact, I'm flipping so fast because this is the part of the model which I really didn't like. At that time, we thought we just wanted to generalize Q-voter model. That's why we made it. So like, at least on one level, we wanted to have original Q-voter model. So we construct this private opinion exactly the same like the Q-voter model was constructed. But from the social point of view, it's not very convincing. And right now we reformulated this model, and I will tell you quickly how we reformulated this. But just now I want to show you quickly results, but also the question we asked at that time. So you may think why we did it like this. I mean, why we updated first public opinion and then private. So we made this model that I called act then think. Maybe I should make it vice versa. Maybe I should first update my private opinion and then the public one. Okay, so I asked several social psychologists, and we also looked through many papers, but it occurs that like in almost every textbook of social psychology, you can find out that it's true that we sometimes stand up for what we believe, but it's also true that we come to believe in what we stand up for. So there are many examples and there are many experiments that shows that if, and this is a very nice quote from this one of my favorite book on social psychology, that if social psychology taught us anything during the last 25 years, that we are likely not only to think ourselves into a way of acting, but also act ourselves into a way of thinking. So you really don't know. It's like your thoughts influence your acting, but also vice versa. So what to do right now? If you are physicists, okay, we just compare two versions of this model. So we construct one version of the model and which one we update the first opinion public and then private and then vice versa. And we did it without any thinking, just we did it. What we measured? We measured several things. So we, of course, measured like the average opinion on this public level. We also measured the concentration of positive private opinion. So in fact, we were counting like all these guys for the public opinion. So we measure how many people has positive public opinion. So all these guys. Then we were measuring this fraction of individuals with positive private opinion. So we were measuring all these guys. But also then we measured something which is called the level of dissonance. So the fraction of people that are in dissonance. So these guys. And this is the measure of this. So what occurred? Okay. First of all, I will tell you, if we put all this thing on the complete graph, so then we have just the mean field approach, in fact. So complete graph means that everybody interacts with everybody. still we have the group of influence, which is Q, which is the parameter of the model. So out of all agents, we are choosing Q, and they influence us. So then, of course, we can calculate everything analytically. I will not show you these equations because it doesn't make sense, but we made it, and we made, of course, also computer simulations. And what occurred? That I have here in this first row, I have public opinion as a function of this parameter P, which is the level of independence. So first of all, of course, we see that we have some phase transition, but it's not that important. The more important thing for now is that if we compare these two approaches, think then act or act then think, then we obtain exactly the same results. No matter if we are dealing with the mean field approach or Monte Carlo simulations on the complete graph. And of course they overlap, because I mean, they should overlap, and they overlap. So exactly the same results. So no matter how you do this, you will obtain the same. Of course, on the private level, this opinion looks a bit differently. So like, let's say majority is higher on the publicly than privately, but still the phase transition is in the same place. And still you obtain this continuous phase transition when the group of influence is equal 5. So this is the smallest number of individuals that influence you that can cause this continuous phase transition. So this is what we saw. I mean, calculations gave us this, and also simulations gave us this. Then we look at the dissonance.
Can I ask you a question? Yeah. How are you seeing the phase transition? Sorry.
Sorry?
How are you seeing the phase transition?
Okay, sorry. So yeah, Piotrek told me that I should make maybe more introductive, and yeah, that's okay. So I have this parameter that is telling me about the concentration of positive opinion in my system, and I see that we have some, okay, and the point 0.5 means that I have the same number of agents that are in agreement with some opinion and against, so like 50-50 state. So if I would measure, for example, magnetization instead of this, it would be 0 instead of 0.1/2. So this line means like complete disorder, in a sense that you have the same number of people that say yes and no. So below some certain point that is here, you see that you have some majority in the system, and above a certain point there is 50-50. So we call it disordered state. So you have phase transition exactly like in the Ising model. So you have phase transition between kind of order, let's say kind of agreement, and disorder, which is like disagreement. Let's say you have 50-50.
Okay, and why is it not going below 1/2?
No, because I mean, it can, in general, for the small system, it can, of course. And as you see, this gray line is showing that you can have the opposite situation, because this system is fully symmetrical. So we don't have any preference for the positive opinion. So of course, exactly the same is for negative opinion. Why I'm showing this like this? Because here you have the line, here you have the dotted line, in fact. So this is unstable point. If you, for the infinitively large system, if you start above this line, you will always reach this state. If you start below this line, you will always reach this state. So this, like the initial condition for simulations, were just that we are above.
Yeah, got it. Yeah, it's the initial condition. Yeah, got it.
Yeah. But of course, in general, this is the gray line, so it can be like everywhere. Yeah, I mean,
thanks.
Yeah, this is symmetrical. Yeah, thank you very much for this.
And here, sorry, another question here. Do you see this hysteresis effect for for Q is larger than 5?
Yeah, like Q equal 5 already gives you hysteresis. So hysteresis you can recognize if you have this jump, like this gray solid line is like the stable solution. So in simulation you will always see this jump, but like this is maybe it's more visible here. So I will make, but it's also seen for q equal 5, but it's more visible here. That if I have something with my pointer, I don't know why.
So your simulations were done with sort of p increasing, or and if you do p decreasing, you would stay on the center line longer.
If I start from the different initial condition, that's why I wanted to change my pointer. So for example, if I will start from for this p, let's say, and if I start from this concentration, of course I will end up on this line. So for this is very good question, and I didn't tell this. So on this picture, what I see from Monte Carlo simulation, I see the results for the initial condition in which all spins are up. So that's why we saw this picture. But of course, in general, like the real results is given by this grain analytical line, and it goes like this. So above this, we'll go to this branch, and below you will go to this. Yes, spontaneous symmetry breaking. Yes, that's right. That's right.
And that property of this hysteresis, that was also already there in the Q-Voter model, or is that really new?
No, unfortunately, it was just the only thing that changed is that it was visible for Q equals 6, not for Q equals 5. So what's changed? Not much, because just the hysteresis appears. So maybe that's why you are not impressed right now, but I will just add one thing, because it changed like by one Q, which is quite obvious, because but at the time we were not interested yet in hysteresis. We were more interested in this internal conflict and so on. So when we were measuring dissonance, for example, we saw that indeed these two scenarios give us different thing. But maybe let's skip to something that is maybe more interesting for you, because I see that time is running out. So I will show you what we came up recently, with what we came up recently. So in fact, this old model was quite stupid, because in our old model from 2018, let me show. We had, like, for example, in this situation, so we are choosing this guy, and I'm asking how do I change my private opinion. So you see, in old model, in this situation, I'm choosing this guy, then I'm choosing this group on free influence, which are these two guys, and because they are unanimous, then I will flip my private opinion to the red one, which is a bit absurd, because on the public level, I'm green. So it means that, okay, it's maybe not completely absurd, but it's a bit strange, because publicly I'm still saying that I'm in favor. I see that others are saying that they are against, and now instead of just saying that I'm against but keeping my old opinion, I'm keeping my old opinion on the public level, but I'm changing my private one. So this was the thing which was completely stupid previously. Okay, another possibility, for example, I'm choosing this guy, and these are two reds. So then, of course, it's quite nice that I was red publicly. I see that all others are red, so maybe I will change also internally, because that I'm behaving somehow, that, for example, I don't know what is wrong with me, but I have only bad examples. Of course, I should not have it. So the first example that came into my mind, that I'm stealing something and others are also stealing, so I start to believe that stealing is good. So this is bad example. But what I mean, I'm behaving in a certain way, others are behaving in a certain way. So maybe I will start believe that this is the proper type of behavior. So in this case, of course, flipping this guy into red would be okay. So, okay, so we did it like this. So in the new model that we are like working paper right now, instead of just flipping in this case, we look at also at our public opinion, and we take into account our public opinion to change our private one. So it's not enough to be in conflict. It's not enough to have private different than public to change my private, but if my public is already the same as other public opinion, then I can change my internal one. And this is something which is called cognitive dissonance, that we have different opinion, we behave differently that we believe, and we always want to minimize our this conflict. So this is how we introduce this cognitive dissonance to the model. And if we do this, then the results are much more spectacular. And I don't have, right now, I have nothing here, so it's really stupid. Okay, sorry for this. So right now, because you don't know what Q is here, so sorry, but if I do this, the Q drops down drastically. So even two people are enough to make this hysteresis. And these are like comparison with the old model. So you saw that like in the old model, we have continuous phase transition, and in our new model, we have already hysteresis, but you don't know what is the Q here, but already Q equal 2 is enough. Okay, so so summarizing, because I should end. So in the end, what we know right now, we know, of course, that the size of the group of influence, as you saw, obviously, is influencing hysteresis. Also preference classification, but not so much. But if we add to this preference classification also this cognitive dissonance, so it's still something which is involved in having two opinions, then we really increase social hysteresis. In my last slide, why do we care about it at all? So it occurs that people from social science use this idea of social hysteresis to answer many important questions. So like quite recent question is why achieving the observable rate of vaccination is challenging, but also what can be the reason of rise of mental health disorders among undergraduate students. As you see, here is quite new from 2018 results published in Nature. And as you see, especially for girls, this mental health increase rapidly. And of course, in diffusion of innovation, which I've been working for years, it's also a very important thing why some ideas and practices and products spread so fast in society, and for other diffusion is hampered. So there are many issues for each. The social hysteresis is really important, and that's why we started to work on this. Thank you very much for your attention, and I hope it was understandable at least a bit, and I hope it was interesting. Thank you very much.
Thank you.
Thanks.
Okay, this is like maybe the slide for the literature. If somebody is interested, some of those things were already published, and some will be published. Okay, and yeah,
so
I'm ready for
I have like
questions.
one question. I didn't understand completely like this mapping from like graphs to something that looked like Ising model. So you mentioned that you have like a Ising type phase transition, but you started with something that is not like dimensional. I mean, graph looks.
But yeah, you don't. Yeah, you don't have to be. So like how this graphs is constructed, you just calculate some aggregated variable. So like, for example, for the Ising model, what you do, you count how many spins are up, and in fact, how magnetization is calculated. You calculate the average position of the spin. So some aggregated variable. And here again also, and it doesn't really matter on what structure you have it. So the Ising model can be put on the, let me go back here. So like the Ising model can be put on the regular lattice, like here. And when we are during the studies, we we learn about the Ising model. Usually we do this on the one-dimensional lattice because we cannot calculate it on the two-dimensional lattice. But like if we are doing like basic Monte Carlo simulation, usually we are doing this for example, two-dimensional lattice. And what we do in the end, we just count how many spins are up. And this is like our measure of the order in the system. If there's the same number of spins up and down, it means that we don't have order in our system. So this is like going from the microscopic state to some macroscopic variable. Doesn't matter if it's put on the lattice or on network, because anyway we just count these guys. Maybe what is not understandable that we have here this Hamiltonian, and here we don't have Hamiltonian. Here we have just some rule. Maybe this is what is, or maybe I'm not getting the point. Did I understand? Did I answer what you asked for, or not really?
Maybe like partially. So you're saying there is some like universality in what you're doing, and then it doesn't matter like on which type of lattice you put your model?
It's not universality, it's just that always I'm counting some average value of something. So here, like average value of the position of the spin, for example, and like the average position of the spin in the Ising model gives me magnetization. This is my my variable. And what I would have then on my graphs would be magnetization as a function of the temperature. Now I have different parameter, which is P, this is some different parameter, and I have another measure, which is the number of spins up. So I always look for some, let's say, aggregated or macroscopic variable, and I'm looking how it changes with some external parameter. But I mean, you can calculate it, of course, but you can just make the simulations and count, like experiment, let's say on computer, and count how many you have, like up and down. I'm not sure if it's clear, but maybe a bit more than it was previously.
If I can ask a follow-up question.
Yeah.
So for these models you presented, you don't have a Hamiltonian for them.
No, I don't have.
There's just some rules, and you update the rules, and that's
yes, and
but,
of course.
I guess you can understand it as a Markov chain.
Of course, I didn't show you, but of course
there's a master equation for them.
Of course, yeah, like all these analytical lines that you saw on these pictures. Of course, I'm not doing nothing else than I constructing a Markov process, and I have transition matrix, transition probabilities between states, and I can write them, and then I can calculate the stationary state out of this. So yeah, exactly. Of course, it's mathematics behind, but not through Hamiltonian, but through the transition matrix. So out of these rules that are given in algorithmic way, if you have this on the complete graph, it's very easy to write down transition matrix. If it's on the more complex network, still we have some approximations that we make, like per approximation we use, for example. So of course, yeah, we can construct some transition matrix, and then we can make calculations.
And your transition matrix is not Hermitian, I guess, in this case.
Not Hermitian? No, why? No, it's Hermitian. Why not Hermitian? Of course it's Hermitian. I mean, yeah. What I would do with complex, no, it's normal. Like they say when I was studying, it's a decent transition matrix. I mean, yeah, it's not transition matrix like in the Ising model, because yeah, there are two types of transition matrix, like the Markov chains with transition probabilities, and I'm talking about the matrix that is constructed out of transition probabilities, not the transition matrix that we are using for the solving analytically the Ising model. Okay, I think that woman is because when somebody is entering and leaving, it's yeah.
Yes, there's someone in my room. Sorry.
She's talking something. Yeah. Yeah. So yeah, we don't have Hamiltonian. We have dynamical rules. We can convert them to probabilities, and then and this is Markov chain. We can calculate everything with the Markov.
But I mean, if you say that your transition matrix is Hermitian, then it's just like a Hamiltonian, right? And then you can.
Okay, so you are saying we could transform it into Hamiltonian.
Yes, if it's Hermitian, you can transform it to Hamiltonian.
Yeah, probably. Although for me, it's never so clear how we can do this. I mean, I don't know, to be honest. But if you have any reference how to make from Hermitian transition, because I believe it's Hermitian. But maybe I was too fast to answering it that this is Hermitian, because in fact I'm never calculating.
It's probably just stochastic matrix, and then
it's not yeah, but it's not stochastic, because every probability, I mean, it's stochastic in a sense that it gives you probabilities, but each probability has a certain it's like the deterministic term for each probability. But to be honest, I was never diagonalizing this matrix. So maybe I was too fast answering that it is Hermitian.
So the lines come from like a mean field analysis, or
lines come from the mean field analysis, yes. But the mean field analysis, so maybe I can even show, I could show some equations. So like I just, because what I have in my system, I can, because at one update I'm changing only one agent. So what can happen with my concentration of upspins, it can only increase or decrease with probability 1 over n, when n is the number of agents. And then I can write down these probabilities, given that I have mean field, of course, limit, because otherwise it's very complicated. So I'm writing just these probabilities that the concentration will increase or decrease. And then from this, I can calculate, for example, expected value of my concentration. An expected value will, in this limit, gives me exactly the same as the average value from the simulations. So for the large system. So I'm just calculating very simple differential equation, and I'm looking for the stationary point. So I'm just looking at the time evolution of the expected value of the C. So this is really, really simple calculation, but in the mean field limit, yes.
If I may ask another question, since our moderator went silent. Well, is there a significance between Q equals 5? I mean, is there a significance about the number in the sense that there's actually some actual sociological data that you sort of spoke about just before your talk that actually says, yeah, that there's some significant thing about Q equals 5? Or?
Yeah, this is very, very good question. So, so what they observe, because they're of course measuring different things. So like, for example, what Dunbar did, Dunbar is the guy who was, it is something like Dunbar number, which is 150, but he was researching also the social networks. And what they found that they have like social circles. The first social circle is 5. This is the closest friends, let's say. The second is 15, and then we have 50, and so on. So like people are measuring like how many people influence us the most. So in fact, this 5 is a bit magical number from some point of view, but also there's some empirical evidence that when we are gathering in groups, like during going out to the city or something, usually, and there were many measurements like in public areas, that the group that is going out is between 2 and 3, like on average. So that's why this 5 seemed for us a bit too big. And that's why we're not that happy with this 5 already, although it appears in social science, the number 5 appears. But like the gathering usually is in this small group. So like having this Q smaller for hysteresis was quite important for us. But like answering in short, yes, there are some experiments that are showing the different sizes of group are causing something. So yeah. Yeah, I stopped sharing, but I can make it again, of course.
I think Han has a question. Yeah, Han, go ahead.
Yes, let me start with one question. So now you have a icing system, but you have you have the private and the public opinion, and then we enter a type of model that we don't know much about it. Because I was thinking during your talk about the random field icing model, because there you have the bias parameter per node, and that could be the private opinion. And then you have the public opinion is just the spin state. And okay, it might be a bit of a stretch, but if you use that model, then you can use all these known results of these type of models.
Okay, to be honest, I was more thinking about Ashkin-Teller model. In Ashkin-Teller model, you immediately have like 2 spins at one node.
Okay.
But talking at the random field Ising model, again, then we have to think about this annealed approach, because like we don't have here a given probability that I will behave in a given way. Like this is the same for the whole system. It's given by some probability. It's still possible, what we are saying, just by doing an annealed approach to the random field Ising model. If it would give the same, I'm not that sure, but I didn't check. So thank you for this suggestion, because what I said at the beginning, my parameter P would be, yeah, I have to rethink. Thank you for the suggestion. I have to rethink. I'm not there is a Ashkin-Teller model who is like immediately with two variables at one node. To be honest, from we were doing also models based on Hamiltonian, but for social scientists they're not that convincing. So like this might be the short way of answering the question. Like if we relate more to the social influence, and like they see this Hamiltonian, it's really difficult to explain them. It makes the same thing. So that's the main reason, in fact, to do it like this. But thank you for the suggestions. So
I have a second question, but I see someone else raising his hand. So
go ahead. Just finish.
Yeah, my second question actually is more general. So in this whole field of social physics, you have this choice between continuous models and discrete models, and you clearly are in the area of discrete models. So why do you I'm confused about this whole choice. So what's your opinion about this basic first step?
Okay, so to be honest, it's still recorded, but okay.
I can stop.
No, don't worry.